Ventilation is the movement of air in and out of your lungs, and it's measured in litres per minute. Ventilation is equal to tidal volume times breathing rate. Breathing rate is measured in breaths per minute. When someone is at rest, their ventilation should be around 6 to 7 litres per minute. When you're not at rest, the ventilation will increase because the breathing rate has also increased. This is because muscles need more oxygen when doing exercise, which therefore means more oxygen needs to be inhaled into the lungs from the external atmosphere, and this would also increase the breathing rate. When doing a sport, your ventilation will differ at different stages. For example, when your ventilation should be around 6-7 litres at the start of the exercise. But during pre-exercise, there is a possibility your breathing rate may increase due to nerves. If you feel more nervous, then your breathing rate may increase. When exercising, your breathing rate and tidal volume will increase as you're in the need of more oxygen and you are producing more carbon dioxide. The longer you exercise, the harder ventilation. As ventilation increases, tidal volume and breathing rate also increases. In a recent test we measured the ventilation of students during the multi-stage fitness test. It is expected that the breathing rate continues to increase as the muscles keep working harder, as well as the tidal volume. As more oxygen is needed in the lungs, leading to the tidal volume to increase. At rest, your breathing rate is around 12 to 15 breaths a minute. However, when you're working maximally, your breaths can go up to 60 breaths a minute. When exercising, a lot of processes need to take place in your body to allow more oxygen in and your lungs to expand. In inspiration, when exercising, your external intercostal muscles will contract, but a lot faster than they would at rest. This goes the same for your diaphragm, when it will flatten quicker than it would at rest and will cause more space inside of the lungs. The volume in your lungs would increase more than it would at rest, and the pressure in your lungs will decrease more in your lungs as more volume is increased. With air, pressure in your lungs will decrease more in your lungs. With air pressure, the concentration gradient will be a lot steeper than at rest due to how high the volume is in the lungs. In expiration, your external intercostal muscles and diaphragm will relax. The ribs will be pulled back in, and the diaphragm will return to a dome shape. The volume decreases the same amount as when I increased, and as it increased, and the pressure increased the same amount when it decreased. Finally, the pressure will be in the lungs into the atmosphere. There will be a steep concentration gradient with the pressure inside the lungs and the atmosphere. In respiration, there needs to be some accessory muscles. These muscles help move the ribs outwards to increase volume in the lungs by contracting and pulling them out. When these stop contracting, then the ribs will just return to its natural position. To trigger these muscles, the centre called the Respiratory Control Centre sends impulses to the muscles to make them contract. The ventral respiratory group is a group in the Respiratory Control Centre, and it controls force expiratory, as it would increase the force of inspiration in order to balance out someone who would not be breathing out more than breathing in. The Valsalva manoeuvre is where people try to do expiration with their noses or mouth shut. This causes air pressure to build. Therefore, pressure increases in your ears and sometimes in your chest. This is done when you're in an aeroplane and your ears have high pressure due to the lower atmospheric pressure when doing the Valsalva manoeuvre. Pressure will equal in your ears and causing it to pop to release the discomfort. Your epiglottis will stop the air from coming out. It slows down your heart being pumped. Out. Therefore, the heart rate will increase. This is good for weightlifting, as you will hold your breath when lifting. When at rest, your breathing rate should be around 13 to 20 breaths per minute. We managed to investigate 2 exercises in order to measure our breathing rate. We did the bleep test and a Wingate test. With the bleep test, the runners would have a low intensity but long duration exercise, because energy systems would not be able to keep up if the runner had high intensity for a long duration. Therefore, as low intensity, the breathing rate will gradually increase. As the graph shows, the breathing rate tends to go up at pre-test as nerves may kick in, such as panicking. This is managed by impulses getting sent to the lungs, which increase breathing rate. Throughout the test, the gradual increase in breathing rate increases ventilation, as well as the tidal volume as more oxygen is needed. The production of carbon dioxide also causes the breathing rate to increase when someone is doing a bleep test, as shown, because more carbon dioxide needs to be exhaled into the atmosphere. This data can also give us an estimation of ventilation, as ventilation equals breathing rate times tidal volume. Therefore, perhaps maximum effort, the breathing rate for this runner in level weight is 50 breaths per minute, and the average tidal rate at maximum is around 3,500 millilitres. Therefore, the runner's ventilation would be 175 litres per minute. At the post test of the bleep test, the breathing rate will be at its highest straight after you've stopped running, as carbon dioxide still needs to be released into the atmosphere. But after a few minutes, it will start to decrease as the muscles are no longer needed for the exercise. Therefore, no extra carbon dioxide is being produced. In the other test we did, which was the Wingate test, this is completely different to the motivated fitness test. This is the maximal exercise, and it only lasts around 20 seconds. The same process will be used for the test and pre-test, such as nerves, and however the only level being used in this test is the post-test, and it was so short and had such high intensity. As a result, the graph shows that the breathing rate is 24 breaths per minute, where it was risen from 21 breaths per minute at the pre-test. This is also increased because of nerves. This is because muscles need more oxygen, but as it is a short period of time, then your breathing rate will not. As it is a short period of time, then you will not need your breathing rate to increase like the runner did in the multi-stage fitness test, even though this is a maximal intensity test. In football, all positions would increase your ventilation as you're running a lot of the time during the game, apart from a goalkeeper. Different positions will have different breathing rates at different times of the match. For example, a winger may have a different breathing rate to a centre midfielder. This could be because the winger may be constantly doing sprints up and down the pitch instead of jogging most of the time. This can relate to the Wingate test, as they are having short bursts of running but at maximal intensity. And maybe a central midfielder will be running like the multi-stage fitness test, constant running but low intensity for parts of the game. The average tidal volume for a footballer will be around 1,500 millilitres sub-maximal, and a maximal would then be around 4,000 millilitres. However, if that happened, then they would fatigue earlier, and they would not last the whole 90 minutes. Therefore, they need to keep their energy quite high throughout the match. In a result of this, if the breathing rate is increasing, then the ventilation is always increasing when the footballer is in a match. When these players are in a game, the movement in their lungs and contractions of the muscle would be very strong, as they have such high levels of oxygen needed and a high level of carbon dioxide being produced, which needs to be put back into the atmosphere. That is why they need to train to enable to make their body fatigue slower.